Okay. So I've seen a lot of you turned in project one, and people are making good progress, and that's great. So at least I know it works in Submiti, and that kind of makes sense as a project. But just in case your only experience with this is sort of maybe like one half a lecture in OPSIS, or I'm not even really sure what was covered, just sort of a quick review. So there's probably 1,000,001 tutorials on writing Echo client-server applications out there in the internet, and you are welcome to look at them. Like, this is, not a thing I would consider cheating. In a language of your choice, if you want to read about a UDP Echo client-server and start from there, that's perfectly fine. They'll all pretty much have the same flavor, regardless of what language you're using, where you're going to have, some client, and you're going to have some server, and the client's going to send a request message, which is the text to be echoed, and then the server is going to send a reply message, which is just the response that contains that exact same text, right? And you can do this, there'll be examples in TCP and in UDP, and for this project, I want you to use UDP, and in fact, for all of the projects in this class, you're going to use UDP. It's because, well, for a variety of reasons. One is UDP it's just a faster messaging paradigm. So it's what's used in industry a lot because the overhead of TCP is not worth it. They'll code redundancy into the application layer. But also it kind of makes your jobs easier. So those two reasons. So the thing about UDP, hopefully you remember from OPSIS, is that it's connectionless. I can spell this. And so what that means, at least for the purposes of what you need to know for this, is that when you send a packet, you need to put the destination IP address and port on the packet, right? So every packet or every message is going to be individually addressed and routed using the information attached to that message, right? And so in our client server application, kind of this Echo client, the way it works is that the first thing the server has to do is has to be, listening for requests. So it's going to listen on what I'm going to call port subscript S. And that's what would be referred to as the server socket. It's not necessarily a different kind of socket, but just the way it's referred to. And so S is listening for incoming messages on this socket. And then the client is going to send a message, right? Send this request message to the server's IP address and the server's port, right? Now, on this message, gets stuck automatically, is going to be a reply, kind of a receiving IP and port. So attached to this message is going to be the IP of the client and the port of the client. Now, this is chosen kind of by the operating system, saying like, what port is available? Here's a port, I'll give it to you. So this is not something that you need to specify. The operating system and the API of your programming language are going to take care of finding a good port for you to use, right? So the client sends this message to the server. The server is going to be listening, on its port. It's going to receive this message. And it's going to then just immediately send the reply back to now the address of the client. So back to the IP of the client, the port of the client, right? And so in order for this to work, basically the client has to send on this IP address and port, and then it has to receive, like look for data coming back on that same socket, right? So the same socket that it used to send the message is going to receive the message, the reply from the server. So it's going to receive the reply. And this is going to be on the same socket, right? And then, in our application, say it's going to print some output, right? And so here is where kind of maybe the harder part about UDP is that there isn't any special blow up message if the server is not available, right? So if you try to make a TCP socket, you try to send a message, you try to create a connection to a server and the server is not there, it's not going to work, right? But in UDP, you're going to say like, here, I'm sending this packet to this IP address and port. That IP, the server that's supposed to be sitting there doesn't exist. You won't know about it, right? So here is where you need a timeout. Just in case S is failed, or the socket's not working or something like that, right? Okay, so that's the basic back and forth. Hopefully when you did the chat server homework 4 in OPSIS, I think this is part of that. Like, it was a much more complicated project, but this was in there. And so what I point out is that what information like do the client and server need to make this happen, right? So they need to know the IP of the server and the port of the server, right? So this IP of S and port of S, this has got to be public information, right? I mean, I don't mean this in any security way, but meaning like the client needs to know this. It can't just guess where it's supposed to send to. So this is what the known hosts file is for, okay? So this is how a server can figure out the IP address of another server. Now, what we gave you is a port range. So, and the port range is going to be 10 ports. You don't need to use them all. You don't need to try them all, right? You make up whatever convention you want. You decide, my server is going to be listening on the first port in the port range. And so when the client tries to connect to the server, to send the message to the server, it knows the first port in the port range is the one I should be using. This is like a contract that you've just established at programming time. There's no secret, right? So I know in OPSIS, you didn't write the client side, so maybe you didn't have control of everything, but now you control both sides. So you get to decide which port they're going to talk on. So that port S, that's something that you pick at design time. You code it into your thing, which port you're going to use. It has to come from that port range because that's what's going to make it available to the to your program. It's not going to be used by any other service or blocked by any firewall or anything like that. But you pick which one you want. Now, this IPC and port C, these are set up, well, the IPC is going to be attached directly. So port C is going to be selected at runtime by your application, and that's fine. So you don't need to do that. The server just needs to know, look at the message, where did it come from? I'm going to send a reply back to that same place that it came from. And that's it. Okay. So any questions about the basics of kind of this request reply in UDP? How invested should we be in the design? Are we going to build on project 1 going forward? So project 2 is not going to build quite on this reply response thing, but project 3 and project 4 will definitely use a reply response pattern, just like in this project, with timeouts. So whether you want to build up incrementally or not, that's kind of up to you. It's probably better to do something solid, but don't over design, because you never want to build more than you need in general. That's like a good programming rule, like KISS, don't do more. So, any other questions about that? Okay. Sorry, so can 2 sites have different IP addresses but the same port range in the autograder? Yes. Yes, that can definitely happen, and that's not a problem because they are in different containers. So they are allowed to use the same port. There won't be any, you won't have a conflict, right? So you can use port 15,000 in container 1 and port 15,000 in container 2, and these are completely, they're like completely different computers. There's no problem with using 15,000 on both of them. So that's why you don't need to try to find a free port. All the ports in the port range are available and free. Okay. And then do we need to create our own known host JSON to set things like our IP address? So in the autograder, it's going to create the known hosts file for you. So it's going to, it knows the IP addresses of the containers, and it creates the known host JSON file to correspond to the IP address of those containers. And it assigns ports to each container that are available for UDP communication. Okay? Other questions about that? Okay, so then I just wanted to, so that's like kind of the UDP part, and hopefully maybe explains the, okay. So if the UDP ports are specified as a range, when the server is trying to send something to a host, would it just try to send the message to every port in that range? Okay, so let's kind of, there's maybe two things in there. So let's sort of like clarify some terminology, at least how I'm going to use it. So the way, just for right now, we're just talking about like a very simple system, not exactly the project. We have one client and one server. So the client sends to the server, and then the server is going to reply. When the client sends to the server, the client needs to know what port to send to on the server. Now, it's not a secret, right? Like you wrote the server, you know what port the server is listening on. Like, so if you have, you get an input of 10 possible ports, they're a list, like they're in order. I'm going to say my server is always listening on the first port in this list. Then the client should be able to also say, I'm going to send to the first port in this list on the server. So there's no mystery. There's no need to try to see what the server is listening on. You get to decide where the server is listening on. Now, when the server sends back to the client, and you don't have to do it this way, but this is kind of the standard pattern. The server is going to look at the IP address and port that were on the message from the client, so this IPC and port C, and use that so that it gets that specifically from the message. It doesn't have to try any port range. Does that answer your question? Okay. All right, so let me a little bit more, and we can ask more questions maybe once we get to sort of more distributed looking part of this, right? But basically, kind of the takeaway message is like you decide how the port ranges are used. You're writing both sides now, so you get to decide what port they talk on, as long as it's in the port range. Okay, so now that's our standard, single client, single server picture. Okay, sorry. If A sends request to B, is it necessary for B's reply to received by A on the same port that A? No. Okay, so this is just one common design, right? The common design is to say it's sort of like a blocking request. So the client sends a request, it blocks reading from that same socket to get the reply. It doesn't need to do that. You can design it another way where it's listening on some other port, but like by default, like sort of the standard, if you look at the standard tutorial, the client is always blocking and reading from that same socket, which is going to be that port that was on the message. If you want to write it a different way where you create like another socket and another port to listen on, that's also fine. Did that answer your question, Josh? Yes. Okay, great. All right, so I'm just telling you, so it can be like, I just described the basic, vanilla echo server that you'll see if you look for UDP echo server in the language of your choice. There are, of course, other variations, you can throw some threads in there if you want. There's many more complicated things. And now what I'm going to describe is like, assuming you find this vanilla echo server and you're like, I get it, this is great. I want to extend this into my project. How do I do this? And this is the most straightforward way I can think of. I wouldn't say it's like the best way, the most scalable way. It's probably a little old-fashioned, but it'll get the job done. So let's just say we have now, my known host file says we have 4 sites. I'll call them A, B, C, and D, right? And so I'll just try to draw the picture of when, now suppose like the user types in the message at client A and says, I want you to send this hello world message to the other sites and get your request. So in this case, client A, site A is going to be the client, right? So this is where like the standard in goes into client A, like you type in, and then we have our other sites. Now they're going to be playing the role of the server, but there's now 3 of them instead of just 1 of them. So client A is going to say, here's a request, and then server B gets the request, does the steps that I just showed above, and sends a reply. You can do to C, and then it gets the reply. And then we can do to D, and we get the reply, and then client A can print out all of the replies, and things are done, right? And of course, you need your timeouts, just like you would in the case of a single server. You'd need timeouts for each of these. So I would say, like kind of like draft 1 of your program, if you're kind of building this incrementally. We can do this. We can send these requests sequentially. Right. But I wouldn't stop there. I think, I mean, we don't want to over-engineer, but I think this is not good enough. So what would be maybe the downside of doing this sequentially? Anybody want to jump in and tell me? All right, so I see timeout waiting, right? Okay, so yeah. Okay, so timeout. So I see you miss messages, the timeout, you don't get a reply, or one doesn't respond. So right now we'll just talk about the timeout. Missing messages is going to come in a second, but that's also something we need to care about. So if the client sends to B and it blocks and it gets a reply, and then it sends to C, it blocks, it gets a reply, right? So if our timeout, which I said is like 200 milliseconds, if we have 10 servers, right, you're waiting longer than the amount of time you're allowed to wait to get all these responses and sort, right? So this just doesn't scale well as the number of servers scales, right? So really what you want to do kind of in your like full credit version is you want to send these requests in parallel. And yeah, this gets a little more complicated. There are many ways you can do this, whether you want to do it event-driven or if you want to do it with multiple threads. And I'll leave this challenge to you, right? But somehow you need to kind of parallelize this, which, you did multi-threaded programming, so this should be accessible. And you wait until you're done with, either timing out or hearing back from every single one of them in the list, and then you sort and then you print. Yeah. I mean, there are many ways to do it. Yep, definitely. Okay, so, but there is still, at least in this design, some blocking, okay? So there's a blocking, even if we parallelize each of these or we had threads for each of them or whatever, right? So we can send a request, block, and wait for a reply. And so then kind of that question comes up is like, okay, well, what if other things are going on? Because this is not a client-server application. This is a distributed application. So like A can be a client and a server, right? At the same time that A is trying to get echo requests handled, B is trying to get echo requests handled. So A is acting as a client, and sometimes it's acting as a server. And so remember when I said there's like a leap you need to make to get from like your client server to your distributed or peer-to-peer kind of application? So it's not a big leap. It's just to turn your mind around, right? So we need A to act as a client. So we have our client code. We need A to act as a server. So we have our server code. We package these up into our single application, right? Great. And then I'm going to run one of these in one thread and one of them in another thread. And so I would recommend this is like my main thread. And this is like a second thread, another thread. I want to say second. Right? So if you've written a client application and a server application, you just put them together, put the server in a threaded function or a runnable class or however you want, and you're good to go. Now remember, there might be like multiple threads inside that are spawned and destroyed or thread pooled or whatever makes you happy. But kind of the driving thread, you would need like two main threads, right? One for the client side and one for the server side. And that's kind of the only like mindset leap from what you've done in operating systems to what you're doing here. That's it. So that's why I was hoping this project wouldn't be too confusing, but I realized the known host support range thing, just for some reason, it wasn't communicated well. So hopefully, does this clarify things? Questions? Any more questions? Okay, so we're guaranteed to have more than one UD port in the port range. You are guaranteed to have, I said 10 ports in the documentation, 10 ports on each site, and no more than 10 sites. I'll say that. So there's going to be at least one port per site. You're guaranteed to have, like, you don't need to use it that way, but like the number of ports per machine and the number of sites, you'll have more ports than sites. Can the client send all requests first? You can parallelize however you want, right? That's fine. You can make a new thread where you send and receive for each one. You can send them all, then make threads that are waiting. Like, you are designing whatever works for you. Are we allowed to make a design that would work on Linux but not Windows? Yes, I will say yes. That's fine. It's SMIDI is always going to be auto-graded in Windows. I will, if I ever need to run anything, my laptop's a Mac. I don't use this tablet for anything, so that's that. I'm not sure like what feature you might use, but if you're looking for some kind of OS interrupt or something that's only on Linux, that's fine with me. Okay. Oh, okay. Well, selecting standard in, but Windows doesn't. Yeah, I guess I just kind of figured you would just keep that threaded, but yes, if that makes you happy with selecting on standard in, that's fine with me. Okay, if it doesn't look at Windows, it's a Windows bug. Yeah, okay. I won't get political about Windows because I don't know enough about it right now. I avoid it except for the Surface. All right. Any other project questions? Okay. When sending a request from the client side, it needs to be within the port range or can be operated side. Okay, so the client, when you create a message, when you create like the outgoing message, don't specify a port. Let the operating system stick a port on there. Then it will be guaranteed to be free. The operating system is not going to pick a port that's not free, and we don't have any like weird firewalls blocking things. So you can just use the automatically assigned one on the outgoing side. Okay, does that answer your question, Mark? So yeah, when you're creating the socket to send, that's going to have kind of like a port assigned to it, right? Automatically, and that's what you're listening on for the receive. So you should never even need to mention a port on the client side of things. Like that should just be like the server has to look at the packet and be like, hey, what port was this sent from? Let me reply to it. From the client never has to look at the port. And this, I mean, if you find any vanilla, like Google UDP Echo server language of choice, like this is how it's going to be done, I would guess, 99 times out of 100. So I think you'll find many examples if you want to look. All right. Other questions? Okay. If things come up, of course, the SMIDI discussion forum is great. So my apologies, like last weekend, I guess I didn't have my like, send me emails when a new thing shows up. So it was like 24 hours, more than 24 hours before I respond, but typically I will respond within like a few hours. So I have everything set up, I get the notifications, and I think my answers have been quicker since then. So please feel free to use that. Like I said, but please don't post your code. And for the most part, like I don't want to look at your code, but like I don't know. There's not much I can do looking at your code, right? We're getting to a point where things are a little bit too complex for someone to just glance and be like, oh, well, clearly you forgot to put the closing bracket, right? So like, it's going to be more conceptual anyway, and it's easier to kind of have discussions on that level. Okay. All right. So next thing I wanted to do a little bit of, I guess, a question. So when I teach this class in person, I write everything down, and typically, like everybody writes everything down that I write down, and I see your beautiful faces in front of me, and I see the tops of your beautiful heads when you're writing, and then when you look back up at me, I know I can move on to the next thing. But I have no idea if anyone's taking notes right now, and I think I maybe assume no one was because I don't think I would. But maybe you are. And so what I want to kind of do right now is just ask. I have a little poll here that's like, do you want me to pause in between writing something down and moving on to the next topic so you can take notes? So if you could very quickly just, hopefully this is the right one, hop on over and fill out this little poll. It's anonymous, and I will just look at it in real time, and then I see a lot of yeses, but like, please just fill out the poll for my, because I made the poll, and I will go from there. I'm going to guess it's a yes at this point in time. And no wrong answers. I'm just trying to do as good a job as I can, because this is a very strange format. Yes, I mean, I know there's the recording, so, but I know I speak quickly, so obviously I think the recording is helpful if you miss something, but I just kind of want to get a general flow here. All right. Of course, I have no idea how many of you are here, but it seems to be an overwhelming yes, please slow down, and give me pauses. So I will try to do that. It might take me a little while to work out like what's the right amount of time, but we'll evolve. Okay. All right, great. Thank you for your feedback. I appreciate it. I will keep trying to improve, but also please be gentle because this is rather stressful, talking into the void every twice a week. Okay, so we're going to move on from the project now. I think that's everything I want to say about the project. Yeah. All right, so now it's been a week, so maybe you've forgotten everything. Hopefully not. We want to go back to vector timestamps. And this is an important topic that pervades all of distributed systems, both in theory and in the real world, is how do we, kind of order events in a system? How do we decide which one happened first, especially because we often, and more likely than not, cannot rely on physical clocks. So we want to come up with a way to order events that's a way that depends on the system, only internal to the system itself. And we talked about Lamport timestamps, and then we talked about vector timestamps. And I'll just maybe review kind of the mechanics of the vector timestamps first. Would anyone like me to rewrite down the algorithm or just kind of do an execution? Please rewrite the algorithm. Yes, no? Oh, sorry, I'm not scrolling. That's what the problem is. Technical difficulty. Okay, I don't think I can pause the recording when I pause. That may be a little bit much, but you can fast forward in the recording for sure. Well, I'll work on it. Okay, execution is fine. Great, so we'll go right to the execution. Okay, so execution-wise, I'm going to draw a picture. So what it is we have a vector that is the same length as the number of processes. So in this case, I have 3 processes, so we start with all zeros. So let me draw my little picture of the execution here. Okay, so there's the execution. All right. A dot after F, thank you. G. No, sorry, that's G, H-I-J. Thank you. This is, you'd think I could copy from my own notes, but not so much. H-I-J. Okay, so the way that this works is that when a process executes an event, the first thing it's going to do is going to tick its own component in the vector, so it means increase it by 1. And then if this is a send event or a local event, then that's just going to become the timestamp of the event. So for event A, process 1 is going to tick the first component, right? So the 0 becomes a 1, the other 2 components stay the same, and that's the timestamp for A. Now, when we have receive, so event H, say down here, let me actually write this in a different color. So when we have a receive, say at H, so the first thing that H is going to do, it's going to tick its own component right before anything. So let's just say here it would become, this is not a timestamp for anything, this is just the intermediate step, 001. This 100 is piggybacked on the message. And then when the message is received, H is received, then it does a pairwise max. And so we end up with 1, 0, 1. Okay. And so does anyone want to tell me for D timestamp? Right. Event D, right? See a bunch. So because this is the second process and it's the first event of the second process, that timestamp is 0, 1, 0. Okay. And then B would be the second event at process 1. So 2, 0, 0. Okay. And does anyone want to tell me what I is? So I is just going to be 1, 0, 2 because it's a local event. So process 3 just ticks the component for its own entry in that vector. And then what about E? So 2, 2, 0, right? Because first thing we're going to do is we're going to tick that 1. So that's going to become kind of like a 2, right? So like a 2. And then it's going to pairwise max between that ticked vector and the timestamp that's attached to that message, and you're going to end up with 2, 2, 0. All right. Questions on the process? Okay, so just like last time, I made another goofy one. You can do your self-check. And link in a second. I just finished this diagram. That's basically my goofy self-check here. Okay. All right, so we'll get back to the lecture. Make sure I'm recording. Yes. So that's the algorithm. That's the brief review. And then last time we talked about, there's a reason that we're doing this. It's not just for, fun with vectors, is that we wanted to maintain order. And so the order that we based on was the happens before relation. We wanted to somehow have these clocks reflect the happens before relation. And I'm going to write this down again because this is, if the most important thing in the class ever. So you can see it as many times as necessary. So we were going to say that two events, E and F, we'll say E happens before F if kind of two conditions, E and F are on the same process and E happens first. I shouldn't say happens, I'll say occurs. Or E is the send and F is the receive of the same message. And then we had kind of this third property, which is the transitivity. If E happens before F and F happens before G, then E happens before G, right? And so this is the exact same thing I wrote before. It's just a slightly different format. And this is just saying, how we want our order to work, right? And so we talked about we want to make a clock that somehow gives us some insight into, we look at two events and we can decide which one happened first or which happened before the other, right? And so we first talked about Lamport timestamps and the weak clock condition. We said that if we use Lamport timestamps, those are the integer timestamps. They're going to give us the property that if E happens before F, then the timestamp of E, and I'll just write this as V for timestamp, but any timestamp that we use, E.V is less than F.V. And we showed that Lamport's timestamp satisfied that. But then we wanted something stronger because this is not a bidirectional, the weak clock condition. We wanted the bidirectional, and that's the strong clock condition. That's if E happens before F, then if and only if the timestamp of E is strictly less than the timestamp of F. And this is why we wanted vector timestamps. Okay? And just kind of a brief review is that if we had two vector timestamps, E and F. What it means for one to be less than the other is you have to have two conditions, one that is less than or equal to, and this is component-wise less than or equal to, and it's not equal to. Okay. So that was kind of, because the background is that we claim, or I claim, that vector timestamps satisfy the strong clock condition. Okay, and this is going to be my theorem. So my theorem is that the algorithm that we just went through, this is going to give me timestamps that satisfy the strong clock condition. And like I said last time, I'm going to prove it to you because this is a theory class at heart. So we're going to write a proof. So because we're proving biconditional, we're going to do kind of your standard. First we prove one direction and then we prove the other direction of the conditional. So for our proof, first we're actually going to show the weak clock condition holds. And to do this, we're going to use, basically we're going to use the definition of the happens before relation, and we're going to build our proof around that, in that we're going to consider, there's three kind of bullet points in the happens before relation. The local events, the send and receive, and the transitivity. So we're going to use those three bullet points to construct our proof here. And so the first one is we're going to consider, it's kind of sort of like local events, but case one, we're going to consider when E and F take place on the same process. So E and F are subsequent events on the same process PI, so they take place one right after the other. And we're going to say E occurs first. Okay. So we want to show that if this happens, then the timestamp of E is strictly less than the timestamp of F. So first thing I want to note is that if we look at the timestamp of F, we look at that ith component of that timestamp, what is that going to be in relation to the timestamp of E? So if I have E.vi and I have F.v of I, so how are they related? Which one's larger? Right, F is larger than E, right? And in fact, because I made them like one right after the other, right, it's just going to be +1, right, because that's the tick, right? Okay. So now I look at the ith component, right? And it's one larger, so we kind of have our strictly larger on that, but we have to look at all the other components too. So what about F.v of j and E.v of j for j not equal to I? So what about the other components? Can we make any claim about them? Right. Well, we can say they're no smaller, right? Greater than or equal to. And why? Well, if E and F are, let's say if F is a send or local event, right, they're equal. Because nothing else changed, right? Like the only clock that ticks for a send or a local event is the I's component. All the other components are the same. And if F is a receive, then we're doing a pairwise max, right? So we can't get any smaller. So is that clear? So definitely we have these two things where there's one component where the ith component, F's timestamp, is strictly larger, and then in all the other components, F's timestamp is no smaller. And that's what we need to conclude that the timestamp of E is strictly less than the timestamp of F. Okay? Okay? So now we're going to look at the second case where E is a send of a message M and F is the receive. And then we're going to do kind of a similar analysis, and we're going to say, okay, well, so we're going to say that the send happened at PI and the receive happened at PJ. So we can say that we look at now the jth component of F. It's going to be bigger than the jth component of E because process J ticked its clock before timestamping F. Okay. And then we want to say that all of the other ones, right? V of say, K, they're going to be less than or equal to F sub V of K. Again, by the pairwise max, because when you make the timestamp of F, you're going to pairwise max with PJ's timestamp and the timestamp on the message, which is the timestamp of E. And so therefore, again, we have the timestamp of E is strictly less than the timestamp of F. Okay. So now I've covered basically the case of like two subsequent events on a single process and the send and receive. And then all of the other things that we need just follow from transitivity. So we can just say that. Other cases follow from the transitivity of both of our operators here. Transitivity of the happens before and the less than. So both of these are transitive, and so we get what we need. Questions about that? And if I scroll up too fast, just give a yell. I'll scroll back down. And by yell, I mean in the chat. Okay, so we went one way, and now we have to go the other way. Okay, so this is what we didn't get from the weak clock condition. This is the other direction. And instead, we're going to prove the contrapositive. Which is what? Anybody? Oh, my Fox people, where are you? Okay. Thank you. Okay. All right. There's a question in there first before we get to the contrapositive. So when I say that, yes. I see some right answers. Thank you, my Fox people, and you other people who didn't take Fox with me. But okay, so let me just address this question first. So when I say that the jth component of E is less than the jth component of F, that the ticket recurs at the receive event before pairwise max is done. Yes, that is the tick that occurs at the receive before you do pairwise max, right? So you're going to increase the timestamp. So I guess another way to think about it is that if you remember, like the jth component of a timestamp at PI is how many events I knows about that happened on J. So if we look at, if that made any sense, but so when E was created, whatever was in this component J, that's like how much PI knew about PJ at the time. It did not know about F, right? Because F obviously is coming later. So when PI sent the message, its value of J had to be less than the value of J when the message is received. The other, because messages travel forward in time. Okay, good. Okay, yes, and I do see some good contrapositives up there too, right? So we're going to prove that not E happens before F implies it's not the case that E of the timestamp of E is less than the timestamp of F. Now, let's just a little bit of math precision here, that this is not the same thing as saying that E dot V is greater than or equal to F dot V, right? So this is not the same thing. Because if you remember that less than relation or happens before relation, those are partial orders, right? So we don't have, it's not the case if one is not less than, then it's automatically greater than or equal. That's not the case with our less than relation here, because we can have concurrent events, and in this case, like neither timestamp is less than the other in this case. Okay, so we're going to prove the contrapositive, and so we're going to look at kind of the premise here, that not E happens before F. So not E happens before F. This can mean two things. It can either mean E is concurrent to F, or F happens before E. So we have to consider both of those. Okay, so let's assume first, so case one, assume E and F are concurrent. And now I make a claim. So my claim is that E and F must occur on different processes. So why is my claim correct? Why can't I have two concurrent events happening on the same process? Yep, parallel can't happen in our model. Yes, exactly. And if you want to define it kind of more formally, is that we actually defined a process as a sequence of events. So it's a total order of events at a process. So they have to happen, if we're going to have two concurrent events, must be on different processes. Okay, so let's suppose, just like before, E occurs on PI, F occurs on PJ. So I guess this one's a little bit, maybe a little bit tricky to wrap your head around, but if we look at the ith component of E's timestamp, just say it's equal to some number K, this means E is the kth event at PI. And if we look at the ith component of F's timestamp, and we'll just say maybe it's equal to L, this means, it's a little bit maybe more fuzzy, but I'll write it. So if the ith component of f's timestamp is L, that means that when f happens at Pj, that the first L events at Pi, those are in some causal chain to event F, right? So somehow some messages has to fly around the system in a way that there's a chain between the first L events at Pi and this F event at Pj, okay? So I'm going to now make another claim that it must be the case that E of Bi is greater than F of Bi. My claim number 2. So does anybody want to take a stab at explaining why that must be true? So what would it mean? So how would F, so this is at Pj, right? F is at Pj. Yep, definitely strictly greater than. Yep. F is at Pj, E is at Pi. They're concurrent, right? So if F's component was bigger than E's component, it would mean that there's a causal chain from E to F. Yeah, there we go, right? E's occurred on Pi, and Pj is not aware of Pi, not aware of E, right? If it were aware of E, they wouldn't be concurrent. And by aware, I mean this causal chain, right? I mean this happens before, this sequence of happens before, so that transitively, by transitivity, there's a chain from E to F. But there is no chain from E to F, which means Pj has no idea that E has happened, like either directly or indirectly. That's what it means for E to have a bigger timestamp associated with it. Does that make sense? I'll write a little explanation. So there's no causal chain from E to F, meaning Pj is not aware that E happened when F takes place. Okay? Now, any question about that claim? All right, well, that's enough. Basically, me for to conclude just based on that, therefore, it can't be the case that F dot, which way did I write it? That E dot V is less than F dot V. Because there's one component in E that's bigger than its corresponding component in F, and that's going to violate the less than relationship for E and F. Okay? All right. So that was the concurrent one. That was, I guess, the hard one. So here's the easy one. So before I wanted to show that, so let's kind of refresh ourselves. What am I trying to show? I'm trying to prove that if it's not the case that E happens before F, then it's not the case that the timestamp of E is less than the timestamp of F. And so I just proved, or hopefully proved vaguely, that if they're concurrent, then this right-hand side holds. And now I'm going to look at, well, what happens if F happens before E? Okay. Now, what do I need to show? I want to show just to kind of refresh our memory. This was kind of where we started. This is what we want to show. That if, so I'm assuming the second case for not E happens before F. I'm saying, okay, well, assume that F happens before E. How can I conclude that the conclusion must also hold? Then the timestamp of E is not less than the timestamp of F. This is an easy one. It's just maybe hard to wrap your head around in this format. If F happens before E, then what can I say about their timestamps? Yes, then by the earlier part of the proof, then we must have that the timestamp of F is less than the timestamp of E, right? This was the weak clock condition that we just proved. And therefore, our conclusion follows that it's not the case that the timestamp of E is less than the timestamp of F. And that's my proof, QED. So, questions about the proof? Yes, I would say it's perfectly okay if it takes a little while for like the reasoning about the vector components to sink in. Like that's fine, not a problem. But I, on the I guess quiz/exam in a week, like I could ask you about this proof, or ask you kind of questions like, well, what happens if I change this part of the algorithm? Does this proof still apply? So definitely you're going to need to understand this proof. It's not just like something for fun, although I guess it's fun, but it is important to understand the steps. So if anyone has any questions, please throw them in the chat or come to office hours discussion forum. I'll add I think there's a timestamps category already. Okay. So then one last thing, I guess I wanted to talk about with timestamps, that is scalability. So is this a good solution? So assuming we buy into kind of the community belief that we do want to keep track of the happens before relation to use it to determine things like who gets a reservation or how do we merge files in a file, like a versioning system, or how do we apply updates in a database, which is very common. We do use this. So how do we, how can we implement this? Is this scalable? And so how do we measure scalability in a distributed system? There'll be a couple of ways, but at least for right now, we want to talk about kind of your standard things like storage. We're not so interested in compute, although it's important, but number and size of messages is important. So we're always going to measure our N, in this case, is the number of processes. So so a measure in terms of the number of processes N. N, right? This is what we're measuring in terms of, right? As opposed to in other classes. So what did you typically measure first by scalability? What I really mean is complexity analysis. How does the complexity of this program grow, or this algorithm grow with the number of processes? So what did you measure? Yeah, I see O of N. I haven't even told you what you're measuring yet, but good guess. Yeah, but so what did we measure in other classes? Like what do we count? Say in intro to algorithms. What was N? Operations. Yeah, size of input, bits, yeah. So all of these things like bits, size of the input, number, usually it's kind of the size of the input, right? And then you count the number of operations and you express that as a function of the size of the input. So we're not really, there's a couple of different things we want to measure, but here we'll talk about message size. So how big is each message? And that is, yeah, we could talk about number of messages. And with the number of messages, yeah. Okay, so I think, John, so we're going to be a little abstract in our messages, and we're not going to like count packets or anything. We're just going to assume you have like an arbitrarily large packet, and we care about like how many things are in it. So this is going to be definitely like a weaker notion of complexity, a weak, more abstract version of complexity, right? So we just care about message size. Okay, so we just care about message size, and I'll come back to your question, Anna, for sure. And that's, in this case, we are going to say like, oh, okay, was that not for me? Okay. All right, never mind. So our message size has n things in it, n numbers, right? So m is going to be, I guess maybe I'm not quite sure what you're saying by the number of additional messages, or what's m in your case here? Oh, about the caps. Okay. Yeah. All right. I don't know. Okay. So I'm not sure what m is here, but we're just going to say that we're going to count the number of things in the message, number of numbers in the message, and it's O of n. Okay. So that's the one thing we want to measure. And then the other thing, at least in this case, is the memory that's used for this. And that's going to be still O of n. Okay. All right. So we have message size, we have memory, and they're both O of n. And so is that good or bad? I don't know. Is it good or bad? Well, I think arguably it's bad, but unfortunately it's also necessary. So as far as we're aware, kind of as a distributed systems community, there is no more efficient way that one can generate messages that satisfy the strong clock condition. Memory is plentiful. Message bandwidth is not plentiful in many places. But n is big, right? N can be big, depends on your system. Internet of Things system, like billions of things. Memory, no matter, right? So we can always add more things, and n is going to scale linearly with the number of things, and that's not great. Gigabit internet, yeah, okay. But so this is arguably not great, but unfortunately, it's sort of what we're stuck with. We can't really do better, and that's the limitation. So. I did see some kind of clever solution using products of prime numbers, right? So you can kind of represent n things using a product of prime numbers, and then you sort of trade off your message size for computation. So there is no free lunch here. We're just stuck with kind of a bad complexity in terms of measuring the happens for relation, but we still do it. And I'm sorry about all of your internet. Okay, let me go back to this question that Hannah yelled at me. Okay. All right. No causal chain from E to F. Are you assuming that because the events are concurrent, so they cannot be causally related nor subsequent on the same process? Why can we assume that about a concurrent events? Subgroup. I am not sure I follow this question. Maybe we should take this offline. Okay, I do appreciate the passion, though, but I think it might be better to do this in voice. I'm not 100% sure I understand. So maybe we'll do this at the end of class. You can ask me. You can put on your microphone and we can chat. Okay. All right, how we doing, kids? We're good? Okay. All right. So that's kind of the end of the logical clocks for now, although, so we've done integer clocks, which are Lamport timestamps. We've done vector clocks. For your project 2, you're going to use matrix clocks. So this is going to come back, but we're going to take a little pause from that for a minute, and we're going to go to physical clocks. So I kind of hand waved around the fact that we needed to have these logical clocks because we couldn't just rely on some absolute source of time. Like that was just not available to us. And it's certainly reasonable to question whether that is a valid assumption or not. And so what we're going to talk about now is if we have physical clocks, how accurate can they be? And so this is physical clock synchronization. And I'll probably start this now and finish it next time. And this will be largely based on the textbook. Section 14.3 up through 14.3.2, but hopefully I say enough in my discussion here that this will be self-sufficient. Okay, so why do we need logical clocks? So why can't we just use the time function and figure everything out? So we all know, at least in our systems, that every process, we're going to assume now, let's just say they have a physical clock. And I'm going to use CI now to refer to the physical clock. And we want our clock to tell us the right time. And so this will be like the only kind of differential equation I'm going to write in the entire course. Hang on, it's a really tough one. And our goal is for that clock to tell me the time, so that at any time t, I look at my clock function and I get out the actual time. So, okay. And you'll hear me refer to this throughout the class, but t, it's what I call wall clock time. This is like the real time, ignoring, like I said, relativity. Let's just assume there is like a real physical time. And so our goal, if we want to write this now, kind of the a differential equation, is that we start with our initial condition that the clock is 0 and our derivative over time should be equal to 1. That's it. That's as complicated as the math is going to get here. So I can draw the pretty picture for those of you who like pictures. There's my clock, right? And the slope of this line should be 1. There's a reason I'm doing this. Okay, that's what we want. But in reality, our clocks don't behave like that, right? So what happens to our clocks? They break, right? But even if they are perfectly working, they drift, right? And that's just, an inevitable function of our clocks. So if you have, say, a computer clock or, a watch, they drift. That means that they don't tick at precisely this rate, like their slope is not precisely 1. Okay, but we don't declare them to be broken, right? Like this is just an inherent part of life. I mean, they could be broken, but like we're still going to say with a little bit of drift, it's not a broken clock. It's just a natural feature of clocks. And so what we define is still a correct clock, meaning like one that meets, say, the manufacturer's specification. It's going to have a bounded drift rate. Okay. So in this case, rho is something that's like specified by the manufacturer. It says like the tick rate, the rate of my clock is going to be within like 1 minus rho to 1 plus rho. And as long as my clock meets this specification, then my clock is correct. It's behaving as I promised you. And so if you think of kind of an ordinary crystal clock, so not your super high fancy one, then rho is going to be about 10 to the negative 6 seconds per second, which just means that you're going to drift by like maybe 1 second every 11 days. right? And that's for like your standard non-fancy clock. But if you have a fancy high precision clock, you can do much better. Rho is going to be, say, 10 to the -7 or 10 to the -8 even seconds per second, right? So obviously this is minuscule. Like this is not a big deal if, after 11 days we're 1 second off. Well, I guess I shouldn't say. Maybe it's a big deal when it comes to like, that really important bank transfer where you need to make sure the deposit came in before the money went out. So even 1 second or, a millisecond can be important depending on the application. But sort of the magnitude of this drift is not very large, but it still means that we do need to somehow correct for this drift periodically. Otherwise, you could get very, very, very far apart if you never correct for this. And so we want to figure out, first question is, seconds per second, right? So every 10 to the negative, it drifts 10 to the -6 seconds for every second. Like you're going to be off, you can kind of go farther away by 10 to the -6 seconds every second. Okay, I just repeated the definition. I'm supposed to make it clear, but there you go. Okay, so maybe if I just draw a picture, we'll get to that eventually. So we could look at this kind of, again, with our plot, that we have our time on the x-axis, we have our clock on the y-axis, and this is our, perfect clock, assuming I drew a straight line with our nice derivative of 1. And then if we look at what can happen is that we can still have a correct clock that can kind of go that way or that way. And then this slow clock would have the derivative of 1 minus rho. And then maybe a clock that's drifting fast would have a derivative of 1 plus rho. Okay. So now we want to figure out, like, given this sort of physical reality that we have to deal with, how often should we resynchronize these clocks, right? Like, how do we want to? And so we have to figure out that after some amount of time, like, how far apart can any clock get, right? So let's say after D time, how far apart can 2 clocks be? So let's say like after, say, time D, how far apart can these clocks be? Anybody? I see T rho, or 2 rho, I'm guessing that's what the P is, yeah. I see 2 rho D. Okay. All right, so for me, who is terribly not good at this, right? What do we have? I will do this the very slow way. So we have our slow clock, let's say, and it's going to tick at a rate of 1 minus rho t, right? And we have our fast clock, and it's going to tick at 1 plus rho. And so, assuming they both start at 0, we're going to just see where they can be at time E. Right? And then we're going to subtract C fast minus C slow of D. And we get, to see the answer, 2 rho D. Make sense? Right. Okay, so a clock drift can fluctuate, right? So it's not a rule that either you have a fixed row. It's saying that you're going to fall in this range, and so like a regular clock could, a real clock could kind of come in and be slow for a little while, then fast for a little while, and then we don't really know where it's going to be. But so what I'm asking, kind of the question is like, realizing it's getting a little chicken scratchy here, but how far apart can they be, right? So in the worst case, they can follow the two outer boundaries, but that's unlikely. But it's possible that happened. Actually, I think this might not be. That picture's fine. So so this is sort of like worst case scenario. How bad can it get? Okay. So then the question is, if I want them to stay within some bound, so let's just say we want to make sure that we don't let, this is a function of d, right? It can get as big as we want, but we want to make sure they don't get too far apart. So we want to make sure that for all of my clocks, Ci and Cj, that we always are less than, let's say less than or equal to delta, little delta here. So how often should I synchronize them? Like assuming I have a magical method to bring them back to the same time, how often do I need to do that? So I want this difference to be less than delta, right? So I want 2 rho d to be less than or equal to little delta, which means that I need to, every little delta over 2 rho time steps, resynchronize. This is the d. The d is telling me how often I should synchronize. And then that will make sure that my difference doesn't get beyond little delta, okay? Okay, does that make sense? How are we doing? It assumes perfect synchronization. Yes, this is assuming perfect synchronization to get that drift, which is maybe a myth, as we'll talk about in a second, but in the kind of, we definitely at least need to do it this often. Yeah. Okay. Maybe I'll just sort of introduce the problem here. So now we've sort of hopefully at least motivated that periodically, regularly, probably quite often, we need to synchronize our clocks. Otherwise, they could just drift arbitrarily far apart. And so we should synchronize them. But even if we can synchronize them, right, as the question comes up, can we get them to be the same, right, accurate enough that we can rely on them for determining bank transfers? This is the question, right? And so I'll just sort of set up the problem here. So what we're going to talk about is how do we synchronize our clock with some clock synchronizing algorithms. And I'm going to talk about, these algorithms are pretty high level. Granted, there are much more sophisticated algorithms in the world that rely on kind of probabilistic distributions and estimations and things. But at their heart, they really have only like two possible flavors. And they have inherently the same worst case error as what we're going to talk about. So you might be able to do better in a probabilistic sense, but if you want to think about just like in the real, if the in fact range of your bad behavior is within these known bounds, then you can get the errors that we're going to talk about. Probabilistically, maybe you can do better, but there is always some probability that you're going to do as badly as we do in this analysis in terms of error. Okay, so I start with this. So we're going to talk about syncing to a time server. So S in this case is going to be our time server. And this is what we're going to consider to be our source of UTC time, which is wall clock, what I've been talking about, wall clock time, okay? So I always ask this because I was amused by it, but does anyone know what UTC stands for? I know now you can Google, so it's not nearly as exciting, but anyone? Universal Coordinated Time, Universal Time Code. Yeah. Okay, so Greenwich Mean Time, but better. Dinner time? I don't know. Okay, so let's see. So this is kind of a goofy story from Wikipedia, but so when they came up with this standard, the English speakers of the bunch, like US, wanted it to be called Coordinated Universal Time, right? And then the French speakers of the bunch decided they wanted to call it, my bad French accent, Temps Universel, yes, Val Coordonné. So this is what they wanted to end, right? So the English speakers wanted an abbreviation CUT, and the French speakers wanted an abbreviation TUC, and so they decided on a compromise UTC, which means nothing. So there you go. It's just a compromise. Okay. Yes. Yay for world peace. Okay. So we want to sync some processes PI, say sync PI's clock to with whatever S's clock, right? This is what we want to do. This is our goal. And we have two ways to go about this. And I mean, arguably this is it, right? There's really not really anything else you can do. The first is called a push protocol or a push approach, which is where you have the server and then you have the process, PI, and periodically the server is just going to tell the process what time it is. And it's going to send a message, and on that message there's going to be a time, and then PI is going to update its clock, right? So it could be that like T is the time at the server, and then PI is going to get this message with the time on it, and it's going to do something with it and presumably update its clock, right? So that's option one. And option two is what's called a pull protocol. And in this case, what happens is PI is going to just say, hey, server, send a request. What time is it? Or what time should I set my clock to? How does this work? And then the server is going to respond and say, this is the time, right? And then the process is going to update its clock in some way. So great. I mean, this looks easy. So what's the challenge? What's the problem here? What makes this a hard problem? Right? Network delay. And not just the existence of delay, right? The fact is we don't know what the delay is. So there's the hard part. And that's where all the statistical stuff comes in, is trying to estimate the delay. But ultimately, like, we don't really get control over it. It can be, it's going to be what it's going to be. So that's the hard part. So this challenge. Okay. Unknown message delay, right? So ultimately, I guess that's probably good. That's about where these algorithms have to come in, is saying, like, given this unknown message delay, what's the best decision I can make about how to set the clock in each of these two models? And that's going to be the algorithm. I think that's probably enough for today. It's going to get a little bit more mathy, and I don't want to lose anybody. So I think I will give you the algorithms next time. So I guess that's it. If anyone has any questions about this part so far. Is the algorithm recovering the basis of the network time protocol? So the network time protocol, yes. And there's actually a discussion about this in the book. So like I said, that there's sort of two underlying fundamental methods, like a push and a pull, right? And this is all there is. But if you kind of try to either query multiple servers or pull multiple times and then develop some statistics that analyze like how these times vary or change or the distribution of them, then you can try to come up with a more accurate estimate. So I'm not going to talk about that in this class, but at the foundation of it is just these, it's just a, I think it's a pull. It's just a pull. There's nothing else you can do. And then the other thing I found out when I was doing my research is that, so RPI, so there's different kinds of time servers that kind of either synchronize to like atomic clocks or GPS clocks. And RPI has a time server, but it's actually like one of the less accurate, so they have certain levels of accuracy, like certain rows that they're guaranteed to have. And ours is not so good. So even if you have access to a time server, that doesn't mean you actually have access to the real time. That's just an aside. Any other questions? All right, so we'll stop now. And then I can take other questions, I guess, as people are heading out. I guess that's it. Okay. What are the best resources to prepare for the upcoming exam? Are there any practice tests? Should we look at textbook problems? Okay. So very good question. Now, I'll sort of, maybe a long-winded answer, but up until this semester, I've called them quizzes, and I still think of them as quizzes. I changed it to exam because once you say like online, open book quiz, it sounds almost meaningless. So I just want to say like these are, they're real things, and you should prepare for them. There aren't any practice tests. I just haven't done anything like that. I think that, the first one I understand can be a little scary. It's really just understand the algorithms and kind of think about maybe corner cases and questions that you have about the algorithms. And I guess I would also say, and understand how they work, right? So like typically I'd be like, fill in the timestamps, right? That's kind of a freebie point, right? So no, and I guess I would say that I know it's scary, but it works out fine every year. And you will, like, the first one is generally like the introductory quiz, so it's not quite as challenging as the other quizzes, and you will learn how the questions work. You will learn how to do this pretty quickly. So I don't know how to say this, but like I don't think there's anything to stress. Just make sure you understand the algorithms and the proof, and there's nothing to memorize. It's open notes, open book. I wouldn't try to make you pretend that you're not going to look at your notes when no one's watching you. So we'll make it open book and open notes. So I don't know if that's the best answer, but all I can say is that it's worked out just fine for the past few years. So I think it'll be okay. Any other questions?
Is now a good time to ask the question from earlier?
Yeah, that's fine. I just want to make sure. All right, so I will stop the recording, I guess.